from n to n plus 1, or from n minus 1 to n, that's the same thing. And we've seen a bunch of proofs like this last time, and we've seen a bunch of proofs like this in the recitation. But what we're going to do today is to show the strong induction step, which is we want to prove not just from n to n plus 1, because that's cannot be done. We need to prove from everything we've done so far all the way to n, 1 to n, proves n plus 1. So I want to do a quick recap of some examples of weak induction first. And some of them were already done. We're not going to do them again. Just to recap that. So examples of weak induction proofs. Some examples that we did. You guys remember we proved that the sum from k equal 1 to n of k is n times n plus 1 by 2. So for one of the formulas we prove it by weak induction because all we had to do in the weak induction step, let's call it induction step here. Weak induction step was to show that, what did we actually show? If the sum from k equal 1 to n of k is n times n plus 1 by 2, then what is Sn plus 1 in here? Sum from k equal 1 to n plus 1 of k is this formula for n plus 1. So that is n plus 1 times n plus 2 by 2. So of course there's a base case in there, or you can take n equal 1 and 2, so on and so forth. There's always a base case. But this proof, what we did was saying if it's true for n, then it's true for n plus 1. That's a weak induction step. Here's another example. We proved that, I think there was a recitation, 5 divides a to the n minus 3 to the n, right? The weak induction step was if 5 divides a to the n minus 3 to the n, then what? 5 must divide? Of course, there's base cases, n equal 1 and 2, but that's the proof that's in the induction step. From n goes to n plus 1. Weak induction, because you only need the last thing to prove the next thing. Here's another example that we did, I think, in class. 1 plus x at power n is bigger than 1 plus nx. If there was a condition here, if x has to be greater than minus 1. The induction is by n. So of course there's base cases, n equals 0, n equal 1. And then what's the weak induction step? If 1 plus x at n is bigger than 1 plus nx, that's the statement for n, then what's the statement for n plus 1? 1 plus x at n plus 1 is greater or equal than 1 plus n plus 1 times x. We did this in class. All these proofs have this feeling of n going to n plus 1. From today, I'm going to tomorrow. It doesn't matter what happened before today. I don't need the other statements. In the induction proofs we're going to do today, we still want to prove n plus 1. That's our goal. But to do so, we can't just use n. We have to use stuff more than n from previous days. From n, n-1, n-2, possibly all the way down to 1. Those are strong induction steps. Let me put here one more that it's in your recitation paper, this week 11, that's due next week. So the last week induction step. Example. I'm not going to solve it, but it's there. It's Fermat's theorem. Remember all Fermat? He'll say if one is between A and P, which is a prime, then what was the theorem statement? Fermat's theorem, yes. What? All right. Fermat's theorem. If one is smaller than A, smaller than P, which is prime, then what was the theorem saying? A to the P minus 1 is 1 mod P. That was the theorem, right? Remember we proved this theorem? We proved it twice with number theory. So in here, I do induction by A over A. So P is fixed. It's a prime number. There's a base case, A equal 1, very easy to prove. And then how the induction step is going to look like? That's weak. Again, I'm not going to do it. That's in your recitation paper. You have to do it by next week. What's the induction over A? If this statement is true for A, if A at P minus 1 is 1 mod P, then what? What's the next statement here? Yes?
A to the P equals 1 mod P plus 1.
P is fixed. It's not induction by P. It's induction by A. So what's the statement for the next A?
P plus 1 to the P minus 1.
A plus 1 to the P minus 1 is 1 mod P. Is the next A, is the next reminder. P stays fixed. P is the number, I don't know, 29. Doesn't move. But A moves from 1 to 2 to 3 to 4 up to, what's the last A that we care about? If P is 29. 28. 28. Because it goes up to P minus 1. So this is very easy. This requires a little bit of combinatorics. You need a binomial formula here. When you do A plus 1, you need to prove that. You know, A you already have because it's from before, but then you need to worry about those factorials. Okay? So all these examples are induction proofs. Weak inductions because it only goes from A to A plus 1 or from N to N plus 1 or from K to K plus 1. Now let's see some strong inductions examples. The proof is the same. We want to prove N plus 1, but it's not enough to use N. We have to use stuff more previous than N. Here's one, which I did on Sunday, so for the few of you who come Sunday, sorry about that, I'm going to repeat this example. We want to prove that 10 to the N is a sum of squares. Sum of two squares. Like a n squared plus b n squared. Integers. When I say squares, I mean integer squares. That's the statement. So let's do a base case. Let's call this example 1. N equal 1, what is this? 10. Is 10 the sum of two squares? Can I write 10 as the sum of two integer squares? What? 1 squared plus 3 squared. Let's do another one. 10 squared, 100. Is that a sum of two squares? Integer squares. can I write 100 as a sum of two squares? I'm talking to the people who did not come on Sunday. Okay, that's 8 squared plus 6 squared. So now I want to do an induction step. I'm going to try weak first, just to show you that it doesn't work. The weak induction, so let's say try weak, would be from n to n plus 1, right? So remember, when you write an induction step of any kind, you have to state down what is it that you're proving. No matter how simple it is, no matter how trivial it is, no matter how obvious it is, when you say induction step, before you prove anything, you have to state, I'm proving from this implies that. So I'm going to say what I want to prove here. Weak induction, it's what? If 10 to the n is some square plus another square, then 10 to the n plus 1 is some square plus another square. I call them bn plus 1, but I don't care who the b is. It's just some square. Right? That's what I want to prove. That if 10 to the power n is a sum of squares, 10 to the power n plus 1 is a sum of squares. Okay, I'm going to try this proof. So I'm going to say, how do I prove this? In an induction proof, we always relate this statement, the n plus 1, with what we already given, the induction premise. Or hypothesis, sometimes called induction hypothesis or induction premise. That's the advantage in an induction step. I already know this, as opposed to trying to do it without induction when I wouldn't know this. So let's try this. This is 10 to the n. How am I going to relate 10 to the n plus 1 to 10 to the n? Well, it's 10 to the n times 10. That's the obvious way to relate what I have to compute here to what I already know. So now by using the induction hypothesis, I replace this 10 to the n with a square plus another square times 10. And this is 10an squared plus 10bn squared. Can I decide somehow that this is a sum of squares now? Is there a way to say this is a sum of two squares? The problem here is it is an integer square. 10 is not a square, right? So when you multiply a square with something that's not a square, you don't get a square. Integers, the way they work, if you want to multiply a square with something, you get another square. This has to be a square. That's easy to prove. That if you take any square, say 25, and I want to multiply 25 with some integer to get another square, for example, 400. What do I need to multiply 25 to get 400? I'm thinking 25, it's 5 squared. Multiply with what to get 400, which is 20 squared? What do I need to multiply with? 16, which is a square. So, but I multiply here with 10, that's not a square. So I'm not saying this is not a sum of squares. Maybe it is, but I cannot prove it this way, right? It doesn't say it's not a sum of squares. It's only saying you cannot make this proof work. How can I prove that this is a square plus another square? Right? That's where the difficulty is. That's what telling me perhaps going from n to n plus 1, it doesn't go very well. How about I try a strong induction? So this doesn't work. It's not like the statement is wrong. The statement is correct. The proof is not. I cannot finish the proof here. So let's try strong induction. Strong induction means I use all the statements from before, not just the last one. So I've got squares not just for n, I got squares for 10 to the 1, 10 to the 2, 10 to the 3, all of them are squares. I want to try to imply n plus 1. So like in all induction statements, I'm going to state very clearly what is it that I'm going to prove here. What I want to prove specifically is, I don't need, induction, strong induction says you can use all of them, but I only care about one in particular, which is not n, like in here. It's n minus 1. So I'm going to prove is 10 at n minus 1 is a sum of squares. Then 10 to the n plus 1 is a sum of squares. So this here, even though I still use only one previous proof, the fact that that one is not the immediately previous one, like n, makes it a strong induction. Any induction step that's not n to n plus 1, it's a strong induction. In here, I could use any n equal 1 or 2 up to n, right? I could use any one of those, but I only need the n minus 1. Because this is an easy example. The reason I need n minus 1 is that instead of multiplying here from 10, I start with 10 at n plus 1, like before. But instead of saying 10 to the n times 10, I'm going to say 10 to the n minus 1 times 100. What's the difference? Why this didn't work, but this will work? Why it didn't work in here? Where did I get stuck? 10 is not a square, but 100 is, right? So if I prove all of them from before, I choose the n minus 1 and say, that was a sum of squares. A n minus 1 squared plus b n minus 1 squared. Multiply with 10 squared, 100. So now this 10 distributes inside, that's 10 to the a at n minus 1 squared plus 10 b n minus 1 squared. That is obviously a sum of squares. So it requires a little bit of creativity. In fact, so I'm going to call this a n plus 1 now, and this b n plus 1. It requires a bit of creativity to say, I tried the weak induction. In most problems, nobody's going to tell you, is it weak induction or strong induction? Well, you're not going to know, right? In the final, you're going to get an induction problem, and we're not going to say it's weak or strong. So trying weak is not a bad idea. See if you can do it. If you cannot do it, still figure out why is it that you couldn't do it. What's the reason that this proof didn't work? That reason very likely will tell you what else do you need in there. Like in here, the reason it didn't work is because 10 is not a square. So I figure, hey, if I start with the previous power of 10, I multiply with 100, which is a square, that's going to work. So that's our first example of strong induction. Here's another one. Example number 2. Any function that satisfies recursion t of n is 2t n by 2 plus n. You remember this recursion? Where this recursion came from? That was the running time. This is the running time for merge sort. Has order, or formally we're going to call this next week something like order of growth. So far I call it order, and next week we're going to formally say what is that order that Virgil keeps talking about. Has order of growth at most n log n. Right? So why do I say any function? Like, is it more than one function in there? What do I mean by that? Any function. That's only one function, no? Or is more functions? Why there's not just one function, but an entire class of functions in there? That's a recursive definition.
Because you can probably like multiply by a constant or add a constant, and it'll have the same like result, even though it's technically a different function.
He's saying there's probably more than one function that satisfies this recursion. If I take whatever function that's good, multiply by 2, maybe I get the same. But in general, when I have a recursion, what else do I need to get an exact function?
Base.
I need a base, right? If I would specify in here a base like what? What's a base?
1, T of 1.
T of 1, T of 2, right? So what I'm saying by any function, I mean any base start. If I start specifying T of 0, T of 1, T of 2, so on and so forth, like the base, then it's only one function. Because given the recursion, if it starts in somewhere, T of 0 equal 5 and T of 1 equal 8 or something like that, then there is only one way for that function to keep growing, right? But I'm not specifying a base. I'm saying I'm going to ignore that because in recurrences, we don't care about T of 0. How does it start? The initial starting point of merge sort, it may be 3 operations or 5 operations. We don't care about that initial start. We only care about how fast it grows. And that's general for all running times. When you took a class, when you're going to take a class in algorithms, you're going to analyze the running time of your algorithm. You're not going to care how it starts, whether T of 0 is 5 or 10 or 20. You're going to care how it grows asymptotically. And how do we say this mathematically? Order of growth is at most n log n. What does that mean? What does it mean? It means to say there is some constant positive, and T of n is smaller always than C times n log n. That's what it means to say the order is not more than n log n. It means to say this function, no matter how it starts, it doesn't matter if T of 0 is 1 or 100 or 1,000,000. There is some constant, so it looks like n log n times something. The constant, it's up to us. We can choose any constant we like, because the order is not changed by a constant. 2n log n, 3n log n, 100n log n, that's all the same order, n log n. But it's not the same as n squared. N squared is a different order. Not the same as n cubed, or 2 to the n, or n factorial. Those are different orders. But within inside the order, you can multiply with a constant and the order doesn't change. So that's what we want to prove here. We want to prove that any function satisfying this must have order n log n or less. The truth is, any function satisfying this has the order exactly n log n. But we're not worried about that, because when we run an algorithm, we care about the upper bound. We care to say, my algorithm runs no slower than that. You know, that's the upper bound. If it happens to be faster, that's great, but what we care a lot in algorithms is to prove that's not slower than something, so to guarantee that's at least that fast. So how am I going to prove this? I'm going to prove it by strong induction. So proof. First of all, how did I guess n log n? How did I know to put there n log n? Why didn't I choose n squared log n?
You're testing it to at most n log n, so you need to do some sort of constant times n log n.
Right, but how did I come up with n log n?
It gave it to you.
Huh?
It told you.
Who told me? No, the problem tells me, right? But I now think about God. God writes the problem, right? How does God know n log n? Remember what we did before to get to that n log n?
Because
Yes.
it splits the input in half each time.
Right, but we tried it, right?
Yeah.
How did we get to n log n? We solved this recurrence before, but now with induction. How did we get to n log n? Anybody remembers? Yes.
We recursively plugged it in like a few times and we found the
We
pattern.
iterated,
We iterated and found the pattern.
right? Remember that when we say, if I iterate the recursion now for tn by 2, I get 2tn by 4 plus n by 2 in here. And I iterate again, I get a 2tn by 8 plus n by 4, and so on and so forth. If I iterate a few times, I get to a general pattern. If you look to your notes from before, I think we did this already twice in class. We get to a pattern that we can solve directly. At the very end, we can say, I think this pattern looks like n log n. Anybody remembers that? Hands up who remembers that. That's how you're going to have to start recurrences. Even though you want to get to n log n, you're not going to guess it unless you start iterating the recursion a few times. Right? So that was just a quick recap. We say T of n is, let me write it differently, n plus 2 T of n by 2. Then we say, okay, that is n plus 2, apply the recursion here. That is n by 2 plus 2t of n by 4, right? Now I sum up the n's, it's an n here. How many n's are here? One n, so that's 2n plus 2t n by 4?
Would be 40.
40. 40, you're right. Let me try to do this better next time. 2n plus 4, I apply the recursion again. That's going to be now who? 2t n by 8. Let's write the free term first. It's n by 4 plus 2t n by 8. So how many n's I have now? 3 n's plus 8 to tn by 8, right? So what happened here, I tried to guess a pattern for after k steps. I looked at this and say, how does this look if I keep doing it for more steps? Is there a general pattern I can guess here? That pattern is an induction kind of guess. If this is the case for after 1 step, after 2 steps, how is it going to look after k steps? Can I guess what this is going to be here, this 3 or the 2? Kn plus, who's this 8? 2 to the k. Like it grows kind of doubles all the time. T of n by 2 to the k. Okay? So now I have to figure out what's the last k. If I got the pattern right, what's the last k? Last k has to be a k such that the inside of t is approximately 1. This thing in here inside the t. Which means k has to be what? How much is k so that n by 2 by k, 2 at k is 1? Log. Log base 2 of n. Generally, when we don't say base, say log, we mean log base 2 in computer science. So that last k will give me what? Log n times n plus 2 at the k is 2 at log n, t of 1. This expression for the last k will be that, which is n log n plus n times t of 1. And this is a linear term. This is an n log n term. So the whole thing, it's going to be order n log n. When we add up two things, the order goes by the bigger term, always. If you have an n squared and an n log n squared is bigger, so you stick to that. If you have a 2 to the n and some polynomial, you stick to 2 to the n. When you add a finite number of things, it's always the bigger one that gives the order. So in here, we can ignore this because the order is going to be dictated by the bigger term, which is n log n. Now, this is a perfect solution to solve this problem. You don't need to do an induction proof. But the problem is, which I'm going to talk about at the end of the lecture today, sometimes when you do these calculations, they can get extremely messy. Right? Sometimes when you go here, you're like, it's a sum of monster sum, and you can't solve it. But you can guess it, you can guess the order. You can, by doing a few iterations, you get a good idea what the order is, but you can't finish these calculations. This is a trivial example for the calculations, very easy. What if I can't finish the calculation, but I can guess the order? I have a pretty good guess what the order is, but I can't do it exact, so I can't finish this proof. What then? I do this instead. I say I guess the order with iterations. I do a few iterations, I figure out the order, and then I prove it by induction. That may be easier than finish up some calculations here. We'll see that in a moment. So independent how I guess this, either the problem's giving me n log n or I guessed it by iteration method. How do I make a proof here? I need a base case, of course. So I'm going to say T of 2 is smaller than Cn log C2 log 2, right? That puts a constraint on my C. Remember this C, the constant? I can choose any constant I want, but I can only choose once, because it's a constant. So once I choose it, C equal 5, I can't change my mind about it. So base case, you say C has to be bigger than, that say C is bigger than T of 2 divided by 2 log 2. Some constraint like that. What's the induction step? Which is my point in this example. From where to where is this going to proof go? This proof is going to go from n to n plus 1? From where to where? In induction step, I can go from all 1 to up to n. I can go to, or say n minus 1, I can go to n. But in this particular example, I'm going to need not all of them. I could use all of them. I need a particular one, which is the one in here that I really need to make this induction proof. Somebody else. So in strong induction, I can use all the previous statements. But in this, looking at the recurrence, there is one in particular that I need to use. Yes?
N over 2.
Correct. So the induction step will be n over 2 goes to n. Informally, that's informal. Formally, how do we say this statement formal? So formal. Remember, you have to state what you prove. In any induction step, you gotta state first, this is what I'm gonna prove. How do I say this, what I wanna prove here for n by 2? That's what I wanna prove. How do I say it for n by 2? T of n by 2 smaller than, I have to read this for n by 2. So what is it?
C n by 2 log n by 2.
Right. That's the hypothesis. That's the statement I've already proven for n by 2. It's one of the statements that I could use. I could use any statement from before now. And I of course I like this one because it relates to my recurrence. And then if this is the premise, what am I trying to prove? T of n is smaller than Cn log n. That is my induction step. It's saying that if this thing holds for n by 2, it's going to hold for n. So it's not from n minus 1 to n, it's from n by 2 to n. And how did I pick n by 2? I look at this recurrence here and I say, how can I relate to something from the past? It's not n minus 1, it's n by 2. That's why I need that one. It's a strong induction because it's not n to n plus 1 or n minus 1 to n. So now how do we prove it? That's what we want to do. We start, of course, with T of n. We apply the recurrence to T n by 2 plus n. Now we apply the premise. We know something about T of n by 2. We know that this is smaller than 2 C n by 2 log of n by 2, right? That's from the induction premise. Plus we have this n here, the extra n. So this is now 2 Cn. I'm going to say this is log n minus log 2. Do we remember that log of n by 2, log of a by b is log of a minus log of b? Hands up. Who remembers that? Log of a by b is log of a minus log of b. And I think I have an extra 2 here. I don't need this 2 because 2 with 2 goes away. It's just Cn. So that is Cn log n minus Cn log 2 plus n. So that is Cn log n I'm gonna say plus n, common factor here, 1 minus, little late, C log. So I got an n common factor, n times 1 is n, and n times C log 2 is this stuff in here, minus n. Right. Now what do I want? Where is this going? Like what I want to prove? I'm going to say want. When I say want on something, it doesn't mean I know how to do it. It means that's my desire. That's what I want to go. So I'm going to say I want to show that this is smaller than what? What is my point to go with this? Where am I going with it? Has to be smaller than what? E of n, E n log n. So I look at what I have and what I want to show, and I'm saying how far away am I from what I want to show?
Very close.
Well, Cn log n is right here. So how can an orange plus a pineapple be smaller than the orange? What's necessary to happen? If an orange plus a pineapple, I want it smaller than the orange, what does that mean in effect? What do I really want here? I'm gonna say that means what I really want, again, orange plus pineapple smaller than the orange. What do I really want? Somebody else. Yes.
You want the pineapple to be negative or
So how is the pineapple negative? N is not negative.
C log 2 has to be greater than 1.
Greater than 1. That's what I want. I can allow equality, right? If it's 1, that's okay, because this can be equal. So now, can I make this happen? What I really want here can be achieved with C. That's equivalent to say C bigger than 1 over log 2, right? How can I make this work? Remember, I can pick a constant.
So pick one bigger.
So I have two constraints. I have this constraint on my constant to make it work, and I have another one somewhere, right? I've got another constraint that says this. Right? So now I say, I can make it work. It works if C is the maximum between those two things, right? 1 over log 2 and T of 2 by 2 log 2. Which it's possible, right? Those are two numbers. If I pick a number bigger than both of them, then both this is going to be satisfied, this is going to be satisfied, my proof is going to work here. Who follow me? Good. So I want to recap something about recurrences. I'm going to go back to this at the end of the lecture. Is this necessary for this example? Is there something wrong with this solution that gets to exactly n log n? No. This solution is good. It actually proves more. This one only proves the order is smaller than n log n, or equal. It's not bigger than that. This one proves exact. From here, I can tell for sure the order is n log n. But in other examples, we're not going to be able to be so sure in here. We still need to do iterations to figure out what's going on. Your problem 3, I think, or 4, 8 t of n by 2 plus n cubed. Anybody looked at that in the homework? You're going to need to do a few iterations to figure out what that is. Anybody figure out what the order is for that? 8 t of n by 2 plus n cubed. That's the homework problem, right? Problem 4 or 3, which one is it? 4, I think. So you got to do a bunch of iterations to figure out the order. And there's two options. Either you do the calculations exact, like I did here, and you obtain the order, and you just say the order is that, assuming you have all these calculations down to here. Or you guess the order, you say, given my iterations here, I believe the order is n cubed log of 2n plus 5. I don't know. I don't want to tell you the answer. You're going to guess it. And then you could say, I'm not going to bother doing all these calculations here. Instead, I'm going to prove by induction that this is true. For all these problems, we only care about order being bounded by something. So you don't need to prove an exact solution for that t. Just like me here, you need to prove an order, an upper bound order. So if you decide it's at most n cubed log 2n plus 5, you need to say there is a constant and t of n is smaller than n cubed log 2n plus 5. Improve that. Or you can do the calculations exact and get an answer here. Either one of those things work. But there's some recurrences for which this is impossible. It just gets out of hand. That was a strong induction example. How about another one? Example number 3. If I have coins, infinite amounts of 4 cents and 5 cents. I only have 2 coins, 2 kinds of coins. Show that I can make change for any n at least 12 cents. In other words, if I have to give change of 12 or more cents, I could make that with coins, with some number of coins that are 4 or 5. So my coins here are weird, right? They're not like the regular pennies and dimes and all that. I only have 2 coins, 4 cents and 5 cents. And I have as many as I want, that's not a problem. Can I make 11 cents? Can you take 4 and 5 coins and make 11 out of it? No. But it turns out you can do anything 12 or higher. So how do we prove this? By induction.
It'd be similar to the 10 to the n equals the sum of squares, except this time we just have the n is just your actual number, that's the sum, and then the sum is the 4 times.
Has to be a 4 times 5. So what this problem is asking, you have to show that n is some number of 4s plus some number of 5s, where both I and j has to be positive, right? You don't care about who I and j is. The problem not asking you to find how many coins of 4, how many coins of 5. This is the number of 4 cents coins. There's the number of 5 cents coins. And we have to show that for any n at least 12, there is a way to do change, right? With some coins of 4 and some coins of 5, right? So I and j's are the coin counts. But they have to be positive, right? You can't do minus 3 coins. So this is a very simple problem if you think inductively. Base case. What's the base case? Where do I start? What's the problem? The problem defines this base case for me.
We gotta start at 12.
N equal 12. Can you do 12 as 4s and 5s? Anybody? How? 3 times 4 plus 0 times 5, right? I'm going to need more base cases here. 12 is not going to be enough. We're going to see that in a second. I'm going to need 4 base cases, right? To see that, before I finish the base cases, I want to do the induction proof. And then you're going to see why I need more base cases. So induction proof, induction step. Can I try weak? I'm going to say again, try weak, just to see what happens. Can I go from n to n plus 1? N to n plus 1 would be if, that's informal. Formal it would be if n is some number of 4s plus some number of 5s, then n plus 1 is some number I prime of 4s, say I2, plus some number of 5s. If I could prove this, that would be a weak induction, right? If you can give, assuming you can give change for n cents, show that you can give change for n plus 1 cents. Right? But this cannot be proven. It doesn't work. It doesn't mean it's not true. it only says that this kind of proof doesn't work. Because n plus 1, how do I relate n plus 1 to n? Well, that's just n plus 1, right? So who's n? I times 4 plus j times 5. And now, can I do something about this plus 1 with my coins? If I already give the change to n cents, say, I have to give 1 more cent, right? Can I give that change of 1 more cent to the coins I have, 4s and 5s? Can I? I cannot, right? Are you guys following me? Trying to relate n plus 1 to n, saying you can give change for n cents, okay, and then figure out the rest, which is 1 cent from n plus 1 to n. That doesn't work. Because this cannot be done. Be done with 4 cents and 5 cents coins. But what can I do instead? Not go from n to n plus 1. Right? I need to go, so this doesn't work, but what if I do strong induction? Strong means I can use everything from before, but I don't need everything from before. I need to go from where to where? From a given n, I need to go to what? What can I do? What this difference of 1, I cannot give it change with constant 4 and 5, but what difference I could?
N plus 4.
N plus 4. Right? If I jump from n to n plus 4, that's informal. Formally, what is it that I want to prove? If n is some number of 4s plus some number of 5s, right? I can do the change for n. Then n plus 4 is some number of 4s plus some number of 5s. That's what I want to prove. That's a strong induction because it doesn't go from n to n plus 1. To be honest, in my country, we don't have this notion of strong versus weak. I only heard that last year when I taught this class. We just call it induction. And this, you have to state what you're proving right there. You don't call it strong versus weak. You just state, I'm going to prove that. And that's it. The first time I heard about strong versus weak was last year when I taught this class.
And when you do it this way, you're only proving it for multiples of 4 of the base case, right?
Well, that's why I need more base cases, right? Now, everybody should see by now why this can work. This is obvious why it works. Because who is n plus 4? Well, that's just n. It's I times 4 plus j times 5, right? Whatever I did change for n, I use the induction hypothesis, plus another 4. So what do I do? How do I give another change to 4 cents? If I could do n cents, how do I do n plus 4? What do I do? How do I do with this 4? What do I do? It's the obvious thing.
You add 1 to I.
I add 1 coin, which is 4 cents. Right. So that is I plus 1, 4 plus j 5s. So that means 1 more 4 cents coin. That proves my induction step. If you can give cents for n, change for n, you can do it for n plus 4 simply by throwing in 1 more coin of 4 cents. But why do I need more base cases? Assuming that's my induction step. That says what? From 12, I have to make a little table here. From 12, it's going to go to, where to go next? 12 is a base case. So what's the next by induction proven? To 12, from 12 to 16. The next one is going to be? Because induction proves all the steps. From 16 I go to where? 20. From 20 I go to where? 28, right? That's only proving these numbers. What do I need to prove? I need to start at 13. I need another base case. Because if I stick with this, I only got n equal these values, right? So I need n equal 13 here. Can you guys do 13 cents? How do I do 13? 2 4s plus 1 5. So if I get 13 as a base case, from 13 I go to 17, right? Because the same induction step applies. From 17 goes to where? 21, 25, 29, so on and so forth. That's still not all the numbers. I still need more base cases because I still miss numbers in here. So the next base case is n equals 14. Can I do 14? How do I do 14? 1 4 and 2 5s. Okay? That 14 is going to say, aha, you start at 14, the next one is going to be 18, 22, 26, 30, so on and so forth. Am I done? I still miss some numbers, so I need one more base case. Which is what? 0, 4 plus 3 5s. And now that I've added 15 to my table here, 15 goes to 19, goes to 23, goes to 27, goes to 31. Am I done? Did I cover all the numbers that are 12 or higher? So, you gotta pay attention to this trick. The problem is not hard, this problem is trivial. The induction step is nothing as a proof. But if this is my induction step, how does this play out to the base cases? Because if I only leave the case n equal 12, and I use this induction step, I'm only proven some numbers. Right? To apply the same induction step, the induction step doesn't tell me you have to start at 12. You can start anywhere you want. Induction step says from n, you go to n plus 4. But I need to start multiple times to do all the n's. I need to start at 12, that's going to cover a range of numbers. At 13, another range of numbers. 14, another range of numbers. 15, another range of numbers. That will cover all numbers now. So I need 4 base cases and a strong induction step. Okay? One more example of strong induction. Last one. That's from your paper, from your recitation 11 paper due next week. Sample 4. If you build a binary search tree, can't write, with n nodes, that means the depth of the tree is at least log base 2 of n. Depth means, from a tree, what is depth? Let's build here a dictionary with what depth means. What is depth for a tree? If I do any tree, it doesn't have to be binary. This tree is not binary. Some tree. What is depth? Depth. Or height, sometimes called. Is the longest path from root, this is root, to a leaf. This is the number of edges on longest path, root, all the way to a leaf. So in this tree, what's the depth? What's the maximum number of edges I can go from root to a leaf, to any leaf? How many? 1, 2, 3, 4. That's the maximum, right? So in this particular example, depth equals 4. Because there are paths that are shorter, but depth is the maximum. It's how deep it goes. 1, 2, 3, 4. And it counts the edges. So root is at depth 0, because it has no edge. These guys are all at depth 1. These guys are at depth 2, 3, so on and so forth. Okay? So in any binary tree with n nodes, the depth has to be at least that. There's no way to draw a binary tree with 100 nodes that doesn't have depth at least that much. So let's do a base case. Let's say n equal, when equal 1, it's obvious, it's just a root, right? What's the depth in here? What is the depth for this tree? 0, there's no edge. And what is this? Log base 2 of 1. By the way, everybody knows what those brackets are? This is rounded down. How is this called? Floor. This is floor. How much is floor of log base 2 of 1? How much is log base 2 of 1 to start with? 0. So that's 0. That works out. How about for n equal 2? How is it going to look? It's a root, and it has some leaf, right? Because it's 2 nodes. What's the depth here? 1. And what is the floor of log base 2 of 1? Of 2. Sorry. Now, the theorem doesn't say those are equal. It says the depth of the tree is at least that value. It doesn't say they're equal. In here happen to be equal. So how do I make an induction proof? I'm going to solve this problem for you guys for the paper. I'm going to need a strong induction. The reason I'm going to need strong induction is because I have the root. Now, this is a binary tree. A binary tree has only 2 branches all the time, at most 2, 0, 1, or 2, right? This is not a binary tree. Anytime you see more than 2 branches, that's not binary. So what happens here, there is a left and right subtrees, right? Let's make it smaller a little bit. And there are, say, P nodes here and Q nodes here. When I draw a tree like that, you don't draw the structure of the tree. You just say there is some subtree. That in itself is a binary tree, right? This whole thing here is a binary tree. Let's call this binary tree left. And this is another binary tree, we're going to call it right. It's an entire tree that happens to stay rooted at these points, these 2, the children of the root. The reason I need strong induction is what? How am I going to prove the statement for n? The total number of nodes in here is n, so total n nodes. That means n is what? 1 is the root. That's the root. Plus how many are in here, right? Plus how many are there, right? If you look at these 3, how many total nodes you have? 1 for the root, P on the left side, and Q on the right side. N must be 1 plus P plus Q. So why do I need strong induction? What my induction step is going to look like? What am I going to prove? How can I relate n? I want to prove the statement for n. This statement. I'm going to relate it to what? The statement for who? For n minus 1? For n minus 2? N by 2? I'm going to relate it to... Remember, in strong induction, I can use any one from 1 to up to n minus 1. I can use to prove the n statement. But who am I going to actually use? You see n minus 1 is going to come into play here? So I need to prove this statement. The depth for n nodes is at least log base 2 of n. That's what I want to prove. The question is, what induction hypothesis am I going to need? That's going to, in an induction step, it's something says, something you proved before implies something you want to prove now. what is going to be the stuff I proved before, meaning smaller than n, that I need to make this proof.
The depth of the.
P and Q. The same statement for those trees. Those are still binary trees, but their size is P and Q. P and Q's are somewhere in here, right? But they're not necessarily n by 2, and they're not necessarily n minus 1, and they're not necessarily n by 4 or n by 8. I don't know what they are. They are somewhere in here. So what I'm going to need to prove is that in the induction hypothesis, depth for P nodes is at least log P, and depth of Q nodes is at least log Q. Is this a valid, strong induction step? In strong induction, I can use any statements I want from before. Yes?
Yes, because P and Q are both strictly smaller than N.
Right. So P and Q are somewhere in here. I don't know where they are. They could be, P could be 3 and Q could be n minus 4 or something.
Now, why do you say that P and Q are not necessarily n minus 1?
They could be n minus 1. Maybe this whole tree has n minus 1 nodes here and no node in here. You could have a tree like that.
With the equation that you wrote, if you just move one to the other side, it's n minus 1 equals
The
P
sum
and
is n minus 1. But each one of them is smaller than n minus 1, maybe.
Q. Right.
Yeah. So
Yeah.
I can't just use n minus 1 to n. I'm going to need P and Q separately. If I only do it from n minus 1 to n, I can't relate to the structure of the tree. To relate to the structure of the tree, which is the same as the recursion before, I need to relate to P and Q. P and Q are fixed, but they're unknown to me. I don't know how this tree looks like. P could be half, Q could be roughly half. That's a balanced tree. Or P could be maybe 3/4 and Q could be 1/4. Or P could be n minus 1 and then Q has to be 0. If P has n minus 1 nodes, Q has no nodes at all. Right? I don't know how this tree looks like, but I know there's a left side of P nodes and right side of Q nodes. And I know I've already proven the statement for those P and Q because they're smaller than n minus 1. In a strong induction step, we say we already proven everything up to n. Who follows me? This would be a great time to ask questions if you don't understand this. Even though we don't know the exact P and Q, like in a recurrence, we knew it's n by 2 that we need. In here, we don't know what we need, but we know it's in this set. That's what makes it still a valid, strong induction step, because P and Q are somewhere in here. So P and Q are definitely from 1 to n minus 1, somewhere. So now, how the proof goes? I'm going to do a little bit, and you guys have to finish it for the recitation paper. I'm going to say the depth of my tree, n, is 1 plus maximum depth to the left, depth to the right. Is this true? Given that this is a tree, what I'm saying, the depth from here to the bottom of the tree is 1 plus whichever depth was bigger before. Is that true? If this has depth of 5 and this has depth of 3, what is going to be the depth of the entire tree? It's just the maximum plus 1, right? Because whatever's the maximum path, it's going to add 1 more to get to the root. Right? So the depth is the maximum left and right, which could be unbalanced, plus 1 more because of this edge. You're going to need a lot of this in algorithms courses and search problems, because every time you implement a binary search tree, you're going to have a depth variable in that implementation. Okay, so what do I know about this? I'm going to assume here, I don't want to write too much, I'm going to assume P is bigger than Q. Because it's a symmetric problem, one of them has to be bigger. So I'm going to say, let's assume P is the bigger one. The same exact proof can be done if Q is the bigger one. So that's okay to make this assumption. One of them has to be bigger. Let's say P is the bigger one. So then, this is bigger than 1 plus max of depth on the left side. Sorry, 1 plus the depth on the left side. Now, P bigger than Q doesn't mean the depth on the left side is bigger than the depth on the right side. Is it guaranteed that if I have more nodes, the depth is also bigger? If I tell you this has 100 nodes, this has 50 nodes, is it guaranteed that the depth on the left side is also bigger? No. This could be a balanced tree, this could be an unbalanced tree. But nevertheless, max of something is going to be bigger than the depth. So this inequality would work because maximum of two things is bigger than any one of them. So whose depth of L according to my induction hypothesis? This is depth of L for P nodes, right? So I know something from the past. My induction hypothesis says for P nodes you get at least that much. So it's 1 plus log base 2 of P, right? Which, if you think of this 1, I can bring the 1 can be brought inside the floor, right? Integers can go in and out of the floor function. So I can think of this as a floor as 1 plus log base 2 of P. 1, I can think of 1 as the logarithm of what? What's logarithm of what gives me 1? Of 2, right? Plus logarithm 2 of P, which is, how much is the sum of two logs? Log of A plus log of B. Log of A plus log of B equal with log of? So that is logarithm base 2 of 2P, because it's a product of them, right? So I already proven that my depth, the one I need, is at least log of 2P. And what I want, I'm going to say again, want meaning I don't know how to prove it. This is what I want to get. What do I want to get? Is this, right? This is log base 2 of n. That's what you have to prove at home. I started you here, like a base case, induction step, how to start. But this, you're going to need two cases separately, n even and n odd. So you have to take those two cases separately to make this proof work. It's simple. I only have it here one line. So to finish this for your recitation paper, you need to say, why is this true? You're going to have to use this assumption that P was the bigger of the two. And say, I got to here, but I want to get to here. How do I finish this proof? Okay? That's what you're going to have to do for next week. So we've got a few induction strong proofs here. And this is particularly very important thing. It shows the how binary search construction of the trees work. How the depth is going to work from one subtree to the next level. Now, our last example of induction, of strong induction, is something very famous in mathematics. And lately we find out it's very famous in nature. It's called the Fibonacci numbers. Those appear very, very naturally in many problems, including anatomy, biology, reproduction, things like that, molecular stuff, geometry. It's not just an abstract concept. So Fibonacci numbers. They define recursively, but it's not the type of t running time that we're going to do. So they define f, the next f of n. Let's just say fn. It'll be easier. It's fn minus 1